Atoms. These things make up so many things in our world. In fact, they probably make up almost all of them. But how do we measure those things? That's what I'll be talking about today. So there are three basic forms of measurement based around the atom. And those things measure its length, its mass, and its amount. The angstrom, represented by an interesting Swedish symbol, I have no idea what to call it, is what we use to measure length. It's a tenth of a billionth of a meter. The metric system, however, was not exactly based off of atoms. It was more like based off of water and space and stuff like that. So it's not really that precise. But the angstrom, we use it to measure the sizes of molecules, the sizes of atoms, the distance between certain bonds and things like that. But we don't get numbers straight on like 1 angstrom or 2 angstroms. Instead, we get numbers like 1.456 angstroms. However, there can be a few exceptions. So when measuring the mass of an atom, some of you might have been taught the AMU, which stands for atomic mass units. Proton is 1, neutron is 1, electron is nothing, or a very small insignificant number. But that's not exactly right, because those numbers are just approximate. What we actually use in chemistry to measure the mass of atoms and molecules in general would be the U. The U stands for the unified atomic mass unit. The unified atomic mass unit, represented by U, is defined as 1/12 of a carbon-12 atom. Now, if you're wondering what carbon-12 is, that's just your common carbon atom. It's just the most common isotope. An isotope is an atom that has more or less neutrons than its most common form. So the oxygen in the air that you breathe is oxygen-16. It has 8 protons and 8 neutrons. Carbon-12 has 6 protons and 6 neutrons. There are many other isotopes of carbon, such as carbon-10, carbon-11, and other things like that. Carbon-14 is an isotope of carbon that we use for carbon dating. So the reason why the mass of carbon is 12.011 is because that's the average mass of all stable carbon isotopes. So the stable carbon isotopes that are there would be carbon-12 and carbon-13. Carbon-14 actually decays, but it has like a really long half-life. So the majority of carbon atoms that we know exist are mostly carbon-12, and there's like a really small minority of carbon-13. So taking the average of those two, like weighing them down and considering how much of them there are, that's why the weight of carbon is 12.011. Now oxygen, which has a weight of 15.999, is just like right off the brink of 16. But oxygen 16 has a weight of 15.994. So the only stable isotopes of oxygen that we know of that we find on this planet that are natural, that is, would be oxygen 16, 17, and 18. So it makes sense. So before I move on, some of you might be wondering why the weight of oxygen 16 is actually less than 16. And if we look at the atomic masses, the proton is actually greater than 1U, save for the neutron, and the electron is still a really small number. And if we add all those up, that actually is greater than 16. So why is that so? Well, there's this thing called mass defect. So if I got 8 protons, 8 neutrons, and 8 electrons all by themselves, and if I binded them all together to create one oxygen-16 atom, energy would be released, and that energy came from the mass, E equals mc squared, you know? And so that's why the weight of oxygen-16 is actually less than 16, because some of the mass was actually converted into energy during the process. If you look at synthetic elements on a periodic table, you can tell that their masses are like just numbers that are right on, but they have parentheses over them, because they're so unstable we don't have enough time to measure their mass. So finally we reach amount. The mole is used to measure the amount of atoms. So the mole, also known as Avogadro's number, is about 6.02 times 10 to the 23rd. So that means that, approximating it, it's 602 with, I think, 21 zeros behind it. So this number is very interesting. And the thing is that because if I had a mole of oxygen, its weight in grams would be 15.999, which, not coincidentally, is also oxygen's atomic weight. That's what's special about the mole. So because the mole works like this, we use the mole for a lot of things, such as joules per mole, grams per mole, liters per mole, and moles per mole. And all of these have a purpose. In fact, there's a whole branch of science that frequently uses the mole. It's called stoichiometry. This branch of science is based off of the law of conservation of matter and is applied when it comes to finding the relative quantities of the reactants and products and of other things in chemical reactions. So I guess that's enough for now. If you liked it, leave a like. If you have any ideas, put them in the comments. Also, feel free to critique me. If you want to check out more videos, go visit my channel. I'll pop the next link to the next video sooner or later. And if you really want to, subscribe. Once again, thank you for watching.